Let's start. Hello, everyone, and welcome to the Quasar Europe Horizon Project webcast, where we will be presenting what are we doing in Quasar and making you a brief summary of the work packages and the state of the work packages that we are doing. So, firstly, who I am. So, my name is Alberto Pico, and I'm Senior Technical Leader in Renewables in Europe. So, I work in EPRI Europe, and EPRI is an electric power research institute that is a non-for-profit organization dedicated to conducting research and development in the energy sector. It focuses on issues related to electricity generation, delivery, and use, with the goal of making energy safe, reliable, affordable, and environmentally responsible. EPRI has more than 50 years of experience. It has been founded in 1972 and advanced energy technologies through applied collaborative research with a budget of approx 420 million, involving nearly 450 entities in about 40 countries. And let's go to the presentation of today. So we will put some background here before. We will see later who we are in the Quasar projects, the challenges that we are addressing, a roadmap and objectives, some project news, and then we will briefly explain the different work packages. So just to put a picture, because a picture is better than 1,000 words, right? So this is the global waste challenge. And we can see that the solar PV, let's say, is a small portion. So the volumes of the solar PV waste are small if comparable with other kind of wastes, but still, there is very important to achieve this reduction of this waste, because we have also key materials here that could be recovered. Also, we need to try to do that this waste converted into resources. So if we see the accumulated PV waste that is expected in the world, or the accumulated PV waste that is expected in Europe, also with a systematic collection of modules plus a recycling rate higher than 85%, we could provide resources to the PV industry demand. So up to a 7% during 2031 to 2040, and up to a 20% of the resources needed during 2041 to 2050. These resources are materials like glass, aluminum, copper, or silver. So, and then what is the PV module challenge? Because it's a multi-layer material sandwich, and this has a lot of complexity. In the PV products, we can classify the modules into the main three categories: silicon-based silicon modules, that is the 97% of the market share. Then we have others that are thin films with a 2% of market share nowadays, and then others that are other type of PV modules. But all of them is like a sandwich of materials. And also all of them, I mean, they have different compositions. So it's quite complex for the recyclers, and there is not any unique solution for recycling this kind of materials. So in Quasar, who we are? So we are a consortium. Quasar is a Horizon European funded project where we have a consortium of different companies that are working there. So we are 19 partners in 9 countries. And the budget of the project is about 7.1 million to be executed in 51 months. So what are the challenges now? So the PV module recycling is a complex nature. So we need to upscale and demonstrate 2 emerging recycling technologies inside the project. Also, the input streams are currently relatively low. So we, in the project, we are setting up a systematic collection and management methodology and decision tools for the end of life of PV modules. The next challenge is that the supply chain needs to be further diversified. So we are addressing this, accelerating end-of-life decision-making by delivering a digital product passport. And also the revenues depend on the recovery of homogeneous and high purity fractions of high-value materials. So we are looking for profitable recycling that enables circular use and resource efficiency of valuable raw materials. And what is the approach? So the approach of the Quasar is based on different objectives, but for example, we have the objective one that is the cost-efficient and transparent management for the entire end-of-life supply chain. So all about from the power plant, sorting, collection, inspection, then going to repair or reuse, recycling, and come back again. So all this cycle. The objective 2 is to promote the repair and reuse in the PV industry. So we are working in also this inspection, repair, use, and the second market challenges. The objective 3 is about what about the recycling? So we are developing and scaling robust and cost-effective and environmentally friendly recycling processes with these 2 pilots. The 4th is demonstrate the circular use of the secondary raw materials. So once we have the output of the recycling, we need to check what are the markets and what is the value of these secondary raw materials on the market. And 4, we promote a circularity by increasing traceability. So we are working in the design for circularity with different initiatives that helps to make better and more circular PV modules. And this could be seen in these graphs, where we have the different work packages are established just to support this process and this flow. So you can see at the beginning that is the supply, collection, inspection, and reuse flow. Okay, in this work package 2, 3, and with these partners that are working on these different aspects. Then, if the flow of the modules are not going anymore to the second market because they are not usable, we enter in the recycling flow. So in the recycling, we are making these 2 pilots. One is made by Rossi with a thermal chemical pilot, and the other is by LuxChemTech, based in a technology that is based on the water jet delamination. Then we will move to the secondary raw materials, where we have all the secondary materials of the output of these renewables recycling technologies. And then we enter in the work package 8, that is analyzing what are the quality of these output materials and what are the markets and applications that where can be used these materials. Then we have the design for circularity, where Solitech and Down are looking for different solutions that are better in the point of the circularity design. And then all of this is supported by different work packages that are helping to the whole project to mapping internal and external end-of-life streams, the waste inventory, and the analyzing of the LCAs and the modeling of the different flows of the materials and the processes on the system. At the end, the objective is just to achieve an eco-efficiency higher than the 70% with the objective 1, with the objective 2, the 3, the 4, and 5 that we have talking about before, right? So mapping all this, we expect that we will achieve an increase of the 70%. And specific objectives are, we expect to reduce the decommissioning cost by 20%. We expect to have module inspection costs reduced by less than 5 euros per module, repair cost of less than 17.5 per modules, upscale the recycling treatment capacity of more than 10,000 tons per year, achieve recycling rates for silicon, silver, polymers, and glass up to 70 to 90%, and then obtain a revenue from recycling materials higher than between 300 and 500 euros per ton. And here we can see some of the advancements, right? We are making inspections, we are analyzing and testing modules, we are also recycling materials, and we are working in the collection and the analysis of all of this. So let's jump now for the different work packages, where I will briefly explain what are the work packages and what is the advance of the different work packages. So the work package 1 is about the end-of-life PV modules, secondary raw materials, logistics, treatment, quality, quantity, and routes. This is a support work package that support all the projects. So the objectives of this work package is to identify and gather quality, cost, and availability information on all possible sources for the needed raw materials located within the European continent, suitable for the processes that will be applied in the ensuing work packages, and securing enough quantity for their execution. The second objective is to model the processes and material flows so that they become quantifiable and reproducible in other geographical locations. Third objective is the screening of possible technological processing combinations with the technical and geographical constraints of each industrial ecosystem considered. And the fourth is study the economic feasibility and business sustainability of the created ecosystems under different supply and demand scenarios. This is divided in 5 tasks: the waste inventory and identification of raw material suitability, the task 2.1, coordination of the material flows and optimization of the processing routes, the flow sheeting for the key processing routes, the industrial ecosystem model, and the feasibility studies. And what we are now, so the waste inventory and identification of raw material suitability. It has been delivered the initial waste inventory that where has been discussed all the end-of-life waste volume accumulation in Europe that will be forecasted for the next years. Also, we are working in the characterization of the recovered samples of the pilot activities that are ongoing. In the task 1.3, we are simulating, making the flow sheet simulations to understand what are the mass and energy balance calculations and all the data that is needed for this process just to simulate and try to optimize it. In the task 2.1.2 is just a coordination of the materials. So who needs what and how we can send these materials to the different partners just to be sure that we can make our task and our works. So for that, we have implemented a wish list to support the material flow of all the projects. The task 1.4 is the model and the industrial ecosystem model, right? So we have modelized all this industrial ecosystem and just delivered, this was delivered to the European Commission. And finally, we are making the feasibility study. We have performed a feasibility study. This has been finished. And in this feasibility study, we have tasks related to the objective 3 and the objective 4 that has been demonstrated that are achievable and are progressing well. For example, this is about the cost-efficient recycling technology. So here you can see how are the percentage of composition of the recovered materials by weight, by market value, and by market value in 2027 and 2031. So here we can see the different materials that can be recovered and the market value that we'll have in the future. So coming to the work package 2. The work package 2 is about the decommissioning and repowering of the power plant. So for that, we have 3 objectives. The first one is establish non-destructive characterization techniques for rapid assessment of the state of health of PV models on the field. The second is a designed cost-efficient decommissioning and repowering routines and logistics. And the third is characterize and quantify end-of-life material streams from decommissioned or repowered plants. So we have 2 main tasks. 2.1 is this best practice, develop a best practice guide for module field inspection, definite categorization, site testing, classing, handling, and storage for utility scale PV plants, mostly on site. And the task 2 is the commissioning and repowering planning cost and material streams, where we will estimate the quantities of end-of-life material produced during the decommissioning or repowering of a PV plant, estimate the decommissioning and recommissioning the repowering cost, and make a decommissioning and repowering best practice. So the task 2.1, it has been finished and is a publicly available document that you can download from our website. The task 2.2, the commissioning and repowering, is a task that is being delivered at the end of May. We are finishing, so we are making the commissioning and repowering quantities and costs that has been finalized, and the final version is being drafted. For example, here you can see some data that is going to be in the output, where we have modeled 4 different plants, and we have estimated the quantities and the cost of each of them. If we go to the work package 3, it's about the product circularity, waste stream information, and end-of-life management. So the objective is establish non-destructive characterization techniques for rapid assessment of a state of health in PV modules in the waste management facility, identify economic options for PV module refurbishment, repair that enable the reuse, develop decision tools for the design and operation of the PV gate-to-grave value chain, so collection systems and end-of-life infrastructure, and establish an online platform for the module digital twins to share across all the value chain. So the tasks are divided in 4. The first one is develop an end-of-life management decision support toolbox. The second one is to establish a product lifecycle information management platform. The third is to make non-destructive characterization techniques at waste management facility for rapid assessment of end-of-life PV modules. And the fourth is in-field or in-factory PV modules backsheet repair. The advancement of these different tasks is like in the task 3.1, we have made the first mathematical model for facilities process and transportation optimization published and delivered. And we are working on the supply chain models and optimization across different end-of-life stakeholders. So here you can see an example. So all the supply chain and logistics is modeled, and we are working on the optimization on that. The task 3.2, product lifecycle information management called the PLIM. So we have performed different meetings. We are working on the platform, and the definition of the architecture has been done, and we are starting in the coding of a minimum viable product where we will have this database where all the different stakeholders could take information, put information, and share with the other companies that were working in the recycling ecosystem, in the end of life ecosystem. In the task 3.3, we are working on the non-destructive characterization techniques and machine learning. For that, we are making a survey between the end-of-life companies, mostly recyclers, and the second-life companies, just to understand what data is important for them, what are the information needed, and what is would be better for them just to improve the recycling or the second use process. Also, we are identifying the data need of the end-of-life processing, and also we are collecting several test protocols and electroluminescent images to develop a machine learning tool to assess the state of the PV module health. So the development of this machine learning has started and is in progress. And fourth, we have the backsheet repair. So in this task, we have demonstrated effective backsheet repair with a flowable silicon sealant by squeeze and spray application on field and on factory. Some repair modules has passed from the class D to the class A module sorting system according to high pot and dry insulation resistant test. So we have demonstrated that continuous compound manufacturer silicon as effective as the batch compounder. And we are in the process of accelerating aging testing in climate chambers just to check the repair modules in the long term. Also, we have established collaboration with similar European projects that are working in similar tasks. So we jump to the work package 4. The work package 4 is the demonstrator of the industrial pilot A, that is a recycling pilot based on a controlled pyrolysis and mild chemistry. The objectives of this work package is upscaling the first generation industrial PV module recycling line at Rossi site from 3,000 tons to 10,000 tons by implementing upgraded continuous process based on pyrolysis. The second is the automation in the loading and unloading of the use, as well as on the handling of different immediate materials along the whole recycling process. The fourth is the implementation of an in situ quality control system, giving feedback on predefined control parameters during the operation of the recycling line. And the fourth is the security assessment and environmental compatibility of the recycling process. So the tasks are divided in these 4 tasks: for the equipment upscaling, for the automation of the loading and unloading, to make the assessment of the security aspect and environmental aspects, and 4, to demonstrate the validation campaign of the industrial recycling line. What is the state nowadays? So we are in the middle of the equipment upscaling from 3,000 to 10,000. So the design of a multi-batch open for a continuous light process and switch from a scrubber filtration technology to a dry filtration technology is in process. The filtration unit has been ordered and will be installed at the beginning of 2025, and the deliverable of this task 4.1 has been submitted. Then in the task 4.2, in the automation of the loading and unloading, the improvements, we have been making improvements on the sorting process from a 99.7 weight percentage purity on copper glass separation. The qualification of new equipment for silicon, fine glass sorting, and elaboration of purchase specifications has been performed. We are working on automated task conveyor installation with an automatic big bag loading, and the engineering of all the loading and unloading system for the pyrolysis oven is in process. Then in the task 4.3, that is the assessment of the security and environmental compatibility, the task has been complete, and we have completed the impact study for a 10,000 tons per year recycling lane, and the conclusion of the task is that the impact is very limited, so it's all approved. Jumping to the work package 5, the work package 5 is the pilot B. So it's merging the lamination and disintegration technologies of end-of-life PV modules and recyclability of the next generation of PV technology. This is based on a technology based on the water jet delamination. So the task is one task, and the water jet nozzle, the task 5.1, the water jet nozzle system is constructed in a way that blasted the materials and remove directly the continuously from the cabinet and the glass pane. So the aim is to increase the throughput, adapting the density of the separation head. So this technology, we are testing it. And as you can see here in the figures, first, it has been proved with one head working and making the delamination of the model. You can see here the backsheet, and here is the glass. So the head goes in the delamination. But then we have explored also the use of several heads just to increase the throughput. So nowadays, the 3 heads pilots is being tested, where we can increase the throughput of the materials, right? The work package 6 is the same pilot, okay, but let's say making different steps. So the objective of this task is demonstrate the separation, sorting, and drying technology for several recovered polymer fractions in this water jet delamination technology. Task 6.1 is further post-processing of blasted materials from water jet and sorting the several foil types. So we can see here some examples. We are advancing on that, and this is the material output that we can achieve with these technologies. The work package 7 is the third part of this same water delamination test. So the object is to improve the purity of recycled materials through utilization of electrical disintegration and survey of the recyclability of next generation solar cells and solar module technologies. The task is about post-process for recycled materials received from work package 4 to work package 7, like plugs and junction boxes. We can see here the status, right? So we are exploring the technology of making a high voltage fragmentation system that uses electrical pulses from 90 to 2000 kilovolts to selectively break materials along their grain boundaries. So this applies a very high voltage discharge in a water environment. The electric pulses create plasma channels inside the materials, and the resulting shock waves propagate along the materials interface, causing the selective fragmentation. Why is the reason for this application? Because if you make a clear separation and you obtain materials with less contamination. The status is that the recovered materials, we have some initial recovered materials for post-fragmentation, including sorting and sieving. You can see here the different samples with different materials. And we are working on that, right? Just to achieve and measure what is the purity of the materials and the weight of any of them. We jump to the work package 8, where we will study the products from a technological value to the market. So this is a very extensive analysis about what is the market value of the materials, and the objectives are to integrate recycled silicon into the metallurgical and chemical silicon routine, to reuse polymeric condensate into the cracker, to chemically synthesize EVA or polyolefins into the wax products, to manufacture PET polymers and recover raw materials from the depolymerization process, to manufacture PER substrates to the specifications of PV backsheets with polymers based on recovered raw materials, to integrate recycled cullet into the float and other glass industries, to reuse recycled silver depending on its modifications in different industrial applications, and to showcase the feasibility of manufacturing silicon modules from recycled silicon raw materials. This is divided in 8 different tasks that talk about these objectives, and I'm going to jump directly to the status, right? So the status quo of these packs is that we are still in an early stage of this work package. We have received secondary raw materials from the different partners, Lux, Rossi pilots, such as silicon, backsheets, EVA, granulates, etc. It has been done mainly a material characterization analysis to investigate the composition of those materials, purity, morphology, using different measurement instruments. Also has been investigated virgin materials flows from various suppliers. We have started planning what type of processing might be necessary for the different silicon materials, and it has been evaluated various depolymerization routes with chemical recycling and the proposed procedures and conditions for the different tests. We jump to the work package 9, where it's called the design and methods for improved circularity. The objectives of this work package is to produce encapsulant-free PV modules, to develop and integrate smart sensors, state-of-health digital product passport, to investigate and disassembly and recycling of PV modules with alternative encapsulants, and to investigate silicon polymers with the bond functionality. The tasks are development of free encapsulant PV modules, smart PV module sensors information management state of art, the study of the disassembly of recycling of glass laminates with alternative encapsulation, and investigating the alternative coating agents to enable easy bypass diode replacement. The task 941, development of encapsulant-free modules, we are advancing on them, and we have made some pilot cells. And we have seen that transparent layers made of several materials with high and low viscosity materials, with coated, with film application tool or dispense. So we have tested different ones. Also, the conductive layers made of paste-like materials, so dispensing and screen printing, lower conductivity than the copper wire, and development of a new module design to reduce the resistance losses. We have here some examples of the pilot that we are performing. On the task 9.2, smart PV module sensors for information management and state of the health, we are working, evaluating the boards that has been assembled. So we have created a proof of concept test that has been done. We have integrated a MNC communication for reading this sensor. The microcontroller programming has started, the data storage components has been tested, and the temperature sensor strip has been designed and assembled inside a module. In the task 9.3, the study of disassembly and recycling of glass laminates with alternative encapsulation. So we have tested with wire saw separation of silicon encapsulated modules that has been demonstrated to be good, to be performed. So one cell mini modules could be separated and not free of a lot of challenges, right, in the process. So ROSI process successfully applied one glass laminate with C-based encapsulants, where we have found that the glass can be recovered, and we have not seen fundamental difference between different encapsulants. And the task 9.4 about alternative coating agents to enable easy bypass diode replacement will start in June, and we have initially checked some materials, and this will advance during the next months. And then jumping to the work package 10, this is the process assessment, TEA, LCA, social acceptance, and circular economy. So the objectives are based on 4: life cycle assessment and eco-efficient analysis, analysis of economic viability, raw materials analysis and optimization of circularity, and social acceptance via involvement of the stakeholders. This is a work package that support all the tasks of the project. So the tasks are the collation and benchmarking of initial LCI data. The task 2 is initial exploitation, business plan, and market and competitive analysis of the whole end-of-life ecosystem. The 3 is the collection of benchmark and initial waste and raw material data. And the 4 is to create some European stakeholder surveys and the first co-creation of the workshop. So the next is the last work package 13, communications, dissemination, and outreach activities. So as every European project, we have a communication and dissemination, and the main objective is just to maximize the project impact through technology transfer and visibility, enable market uptake inside and outside the consortium, raise awareness of the interest from markets, stakeholders, and policymakers, promote the circular economy in the PV via education, outreach, and disseminate knowledge. This webcast is part of this work package where we try to disseminate what are we doing in the project, and also you can find more information in the next slide where you can see the different actions that we have taken and what are the upcoming events. So here is the project. We invite you also to visit our website. You can search it in the Quasar EU project. And also we have a LinkedIn profile. So you can join, and here we will be posting regularly the different updates of the project. So thank you very much. And let's see if you have any questions or something on the question and answers. And if not, this will be the end of the webcast. Thank you very much for being here. If you have any doubt, you can write on the question and answers. If not, also you can send us some communication through our LinkedIn channel where you can contact us, and we will be very happy to share information and insights with all of you. So thank you very much and have a nice day.